Hi guys, welcome back. In this very short lesson, I hope we will define the term multiple and factors and what we mean by prime factors, in fact what we mean by prime numbers before we look at prime factors. We will also express any number as a product of prime factors. We will define what we mean by LCM and HCF. And finally, we will use this knowledge or these skills to solve some real life problems. Okay? So let's just begin. Before we go into discussing multiples and factors and even LCM and HCF, I think we need to remind ourselves of what we mean by positive integers or sometimes what we refer to as counting numbers or natural numbers. So of course the positive integers or the counting numbers are the numbers 1, 2, 3, 4, right? So the positive numbers, we exclude 0, 1, 2, 3, 4, 5, and so on, are referred to as counting numbers. In order to define multiples and factors or divisors, we need to be making use of these counting numbers or positive integers, okay? And so let's talk about what we mean by multiples. So the multiples of a number are the products of that number and these positive integers, okay? So if we multiply any number by these counting numbers or positive integers, what we end up with are what would be referred to as the multiples of that number. So for example, the multiples of a number n are the product n times 1, n times 2, and so on, right? So like that. Multiples of n there are n multiplied by 1, followed by n multiplied by 2, n multiplied by 3, and you can go on to infinity. All those would be the multiples of n. Here are some examples. So what are the multiples of, say, a number like 2? Well, the multiples of 2 are 2 times 1, 2 times 2, 2 times 3, and so on, right? So 2 times 2 is 4, 2 times 3 is 6. Okay, and we can go on as far as we want, okay? So in short, the multiples of 2 are 2, 4, 6, and so on. Every time we multiply the integers by 2, we end up with the multiples of 2, okay? Similarly, the multiples of 3 can be expressed as 3, 6, because 3 times 1, 3 times 2, 3 times 3, and so on, okay? And the multiples of 5 can also be expressed in the same way, 5 times 1, 5 times 2, 5 times 3, and so on. So these are called the multiples of 3, all right, and the multiples of 5. Good. Let's see if we understand what is going on here. So let's just build on what we have understood. Okay, let's list the first 10 multiples of each of the following numbers. So I have 3 there, and I have a 4. We want to list the first 10 multiples of 3 and of 4, but this is not where we want to end. We want to try and build on this understanding. All right, so the multiples of 3 and the multiples of 4, and then we want to list the multiples that are common. So once we've determined the multiples of 3 and those of 4, we will see which multiples are both in 3 and are also in 4. In other words, the intersection of the multiples of 3 and the multiples of 4. Okay, and after that, we will find out which of those multiples is the smallest or the least. And notice that I have written L there. I've expressed that in orange so that we remember what that means. Okay, so let's, you can pause the video and try solving this, answering this question, and then follow and see if we are getting the same results. Okay, so multiples of 3 then, we know the multiples of 3 are 3 times 1, 3 times 2, and so on. So I'm listing them there. Okay, those are the multiples of 3. And the multiples of 4 is 4, 8, 12, and so on. So the multiples of 4 are right there, okay? And the next part is saying, hence, list all multiples that are common to 3 and 4. So which multiples are here and also down there? Okay, and if we look carefully, I think the first one I see there is what? There is a 12 up and there's a 12 down there. So 12 is a common multiple. We can list it down there as a common multiple. The next one is 24. And if we were to go on with the top one, I suspect the next one there would be 36, which would be common with the 36 on 4. And so we can say that the common multiples, common for C there and multiples for M, so CM for common multiples are 12, 24, 36, and so on. Okay? And part C is asking which of these numbers, the ones we've listed down here as common multiples, is the smallest. And clearly the smallest of them there, or the least of them there, is 12. And so we can conclude that the least or the smallest common multiple of 3 and 4 is 12. The least of the common multiples. So the least L of the common multiples, which is LCM, the LCM of 4 and 3 is actually 12. And that would be our conclusion. And that's actually what we mean by LCM. Okay? Let's move on. Here's a question to check your understanding. Using the previous method, find the LCM of the following sets of numbers. So we have we want to find the LCM of 3 and the LCM of 5, and then we want to find the LCM of the set of 3 numbers there. If you've done this correctly, you should end up with an LCM. So pause the video, of course, and try it yourself. And if you've done so correctly, then you should end up with LCM of 15 for 3 and 5 and an LCM of 30 for 2, 3, and 5. Okay, let's move on. Here's a second question. Here, I just want you to think about it and see the kind of work involved. We don't have to solve it. You can try and solve it using this method we've been using, but otherwise you don't have to. What is the LCM of 82 and 96? So you can see that these are slightly larger numbers compared to 3 and 4 that we did earlier. All right. Well, to do so, if we try the same method, we would have to start with the LCM of 82. That means we are looking for 82K. So 82 times 1 is 82. 82 times 2 is 164. 82 times 3 is 246, I think. 246. 82 times 4 would be 328, and so on. But you can already see that we have to think about those multiples, okay? Which is something I would not want to do, all right? When the numbers are very large, we don't want to be doing this, okay? Moreover, we may have to go into, we may have to have like 100 of them before we get something that is actually common with the 96, all right? And that is a lot of work, also very, very tedious, right? Mathematicians don't usually like to work with tedious methods, okay? And therefore, we must find a way of solving this kind of a problem. When the numbers are large like that, we must come up with a way of finding the LCM without this kind of tedious processes, all right? We're going to look at that very, very soon. In the meantime, I want to introduce something else. So we know what we mean by multiple, and we know what we mean by LCM, the least common multiple, right? So now let's talk about the next thing, and that is divisors, also called factors sometimes, okay? All right, so the question is, and again, I just want us to think about this. The question says, list all the positive integers. Normally, divisors don't have to be positive, but to make our life easier for the time being, let's just think about the positive integers one more time, okay? So list all the positive integers that can evenly divide 8 without leaving a remainder, okay? Which are these positive integers that would divide 8 without leaving a remainder? So I'm going to try positive integers starting with 1, and I will increase them and see which ones can divide 8 completely without a remainder. Okay? And I'm going to list those, and those are going to be the divisors of 8. Okay? So let's start with 1. We will put the list up there. If we put 1 there, can 8 divide 1? Okay? Can 1 go into 8, a fixed whole number times? And the answer is yes. 1 goes into 8 times. In other words, 8 divided by 1 is 8. So there is a complete number of times 1 goes into 8 without leaving a remainder. And for that reason, 1 is a divisor of 8. Okay? So that gives us 8, and therefore in the list we can put 1 as a divisor of 8. Okay, what about 2? So we will go in the order of positive integers. Okay, so what about 2? If I divide by 2, I will get 4. So 2 goes completely into 8 4 times without leaving a remainder, and therefore 2 is also a divisor of 8. What about 3? If I put 3 in there, well, 3 does not go into 8. In fact, if I 8 divided by 3 is going to give me 2 point something, which clearly is leaving a remainder. The fact that we're having a decimal number there means that a remainder is left, and therefore 3 does not obey this rule. It leaves a remainder, so 3 is not a divisor of 8. Okay, how about 4? If I try with 4, 8 divided by 4 gives me 2, so it goes in completely, and for that reason 4 is a divisor of 8. And lastly, well, not lastly, that was 4. How about 5? If we divide by 5, again you can see that that's going to give me 1 point something, which means it's a remainder. Alright, 5 is therefore not a divisor of 8. Similarly, 6 is not a divisor of 8. Okay, 6 is not a divisor of 8 because 6 will also be 1.33. We have a decimal number left behind, so 6 is definitely not a divisor of 8. We can try 7, and again 7 is not a divisor. It gives us a decimal number. And lastly, what about 8? So we will go on until 8, because above 8, those numbers cannot go into 8, right? So the last number then is 8. Does 8 divide 8? And the answer is yes. 8 goes into 8 once, and therefore 8 is a divisor of 8. Okay? And so we can say that the divisors, also known as factors of 8, are 1, 2, 4, and 8. In fact, the factors of a number are among the factors of a number, there will be 1 and the number itself. So 1 is always a factor of any other number, and the number itself will also be a factor of itself. Okay, so a number may have several factors, including 1 and itself. Okay. Let's see another example. You can try other examples, 6, 15, whatever number that you want to try. But let's also try some algebraic expression. Okay, list all the divisors of 2x. Can we find all the divisors of the divisors? Can we find all the divisors of 2x? Okay, so we'll have 2x in the same way we did it earlier. And we start dividing by positive integers, although we don't have to only divide by positive integers, right? That's going to be our list. So this is a bit kind of extended process. So does 1 go into 2x? And the answer is yes. 2x divided by 1 is 2x, and therefore 1 is a divisor of 2x. Does 2 go into 2x? And the answer is that yes, 2x divided by 2 is going to be x, and therefore 2 is a divisor of 2x. The next thing we try is x. Does x go into 2x? Okay, and clearly you can see 2x divided by x leaves us with 2 there, and therefore x is also a divisor of 2x. Okay, and lastly, we try 2x itself. Does 2x go into 2x? And the answer is yes. 2x divided by 2x is 1, and therefore 2x itself is a divisor of 2x. So you can see again that 1 and 2x itself must be part of the divisors of the number 2x. Okay, so we can conclude then that the divisors or the factors of 2x are 1, 2, x, and 2x itself. Okay, all right, let's see if we are understanding this. Here's a question I want you to try. You will pause the video, try it out, and then check what the results are. List the divisors of the following numbers or algebraic expressions. So we want to list the divisors of 10, the divisors of 12, the divisors of 3x, and the divisors of 4x squared. Please pause the video and try it out yourself, and then see if these are the answers that you get. Okay, so from my side, the divisors of 10 are 1, 2, 5, and 10. Notice that 1 and 10 are a member of the set of divisors of 10. Okay, 12, the divisors of 12 are 1, 2, 3, because 2 goes into 12, 3 goes into 12 4 times, 4 goes into 12 3 times, 6 goes into 12 twice, and 12 goes into itself once. Therefore, these are the factors or the divisors of 12, and again you can see that 1 and 12 itself are part of the factors of 12. So there may be others, but 1 and 12 must also be included. So I expect that one of the factors here is going to be 1, and the last one is going to be 3x itself. Similarly, one of the factors here is 1, and the last one must be 4x squared. Okay, so what are the factors of 3x? If you've tried this out, you should find that they are 1, 3x, and 3x. So notice 1 and 1x, 3 and 3x. There is a pattern to determining the factors of an algebraic expression such as this. Okay, so similarly, that goes the same way with 4x squared there. What are the factors? And if you've done this correctly, this is what you should find. See the pattern? So for 4, there is 1, factors of 4 there are 1, 2, and 4. And then because we have x, we must have 1x, 2x, and 4x, which is what you have here. And then we must have, because there is an x squared also, we must have 1x squared, then 2x squared, and 4x squared. So that's how you determine those factors. All right, let's move on. All right, so divisors, how do we define divisors for a number? And we say that a number or an algebraic expression that divides another number or expression evenly without leaving a remainder is a divisor or a factor of that number. I don't know if that was clear. Well, but if you consider what we've done earlier, hopefully that was clear. All right, let's build on our understanding then. Two sets A, B, and C, well, 3 sets clearly. 3 sets A, B, and C, so that should be 3 because we have A, B, and C, are given as follows. A are factors of 12. The set A is the set containing factors of 12. The set B is the set containing the factors of 16. And the set C is the set of A intersection B. Right? Hoping you remember what we mean by A intersection B based on previous topic on sets. List the elements of each set. Right? That's the first question. The next question is hence to state the highest or the greatest or the largest element of the set of inside C here. right? So once we've listed this set, the set of common factors, in other words, when we say intersection here means the elements that are here and also here, and that is the set of common factors, all right? So we will state the highest of the elements of the set C, okay? All right, so this symbol means intersection, just as a reminder, which also means that we are looking for the elements that are common to set A and set B, okay? Let's do that. So pause the video and try it out, and then let's see if we get the same results, okay? So the first part is asking us to list the elements of each set. So the elements of set A means the factors of 12 must be 1, 2, 3, 4, 6, and 12. I think we did this earlier. And the factors of 16 would be 1, 2, 3 is not a factor of 16, so the next one is 4, and there is no other until we get to 8 and 16 itself. Then the question is, which of the elements of set A, the factors of 12, are also factors of 16? And you can see 1 is there, 2 is also common, and 4 is also common there. And so we can list the common factors as 1, 2, and 4. Please check carefully and see that we get the same thing. And then the last question then, we should state the highest or the largest of the elements of set C, and that largest element of set C is 4. Okay, so we can say that 4 is the highest of the common factors. Okay, so 4 is the highest of the common factors of A and B. We refer to this as the HCF, the highest common factor of 12 and 16, also sometimes called the greatest common divisor, because we said factors are also referred to as divisors, so we could refer to this as the greatest common divisor of 12 and 16. I hope this is making sense. Let's move on. So let's talk about HCF proper. In fact, what I want you to think about these questions. Find the highest common factor, or if you like, the greatest common divisor of 9, 12, and 15. Pause the video and try this out using the method we've used earlier. Okay, if you've done this correctly, then your answer should be 3. Now let's see how I got 3, because we've only done an example 1, so let's see how we got here. All right, let's see how we got the highest common factors of 9, 12, and 15. So of course the first thing is to find the factors of each of them. So factors of 9 are 1, 3, and 9. Factors of 12 are 1, 2, 3, 4, 6, and 12. And the factors of 15 are also given there. We want first of all the common factors before we pick the highest. Which are the common factors? Okay, which ones are common? And you can see that 1 is common there. You can see 1 in each of them. And we can see there that 3 is also common. There is 3 up there and in the middle and the lowest level. And so 3 is also a common factor. I don't see any other common factor there. And so the highest of the common factors, okay, and so the highest of the common factors, HCF, must be 3. Okay, and so we can conclude that the HCF, the highest common factor of 9, 12, and 15, is 3. Okay, right, here's another one. Find the highest common factor of 12, 18, and 30. And in the same way, okay, pause the video and try it out. If you've done this correctly, you should find that the HCF of 12, 18, and 30 is 6. Okay, how did we get that? Let's see if you did the same. First of all, we listed the factors of 12, of course, we've already done that. Factors of 18 are given there. Check that they are exactly the same thing as I got them, that yours are the same. The factors of 30 are listed there. And now we need to list the common factors. First, we must list the common factors and from there pick the highest, okay? This is just about understanding. Eventually, we'll find better methods of finding the HCF, all right, without having to have a large detail of listing the factors of each of them like this. There is a faster way. But in order for us to understand what's going on, what we mean by factors, and to understand what we mean by the common factors before we talk of highest of the common factors, it is important that we do this, okay? So which of the factors are common in this case for 12, 18, and 30? Well, clearly you can see 1 is common there, and 2 is common, right? You can see the 2 there is common. 3 is common. As you can see, we can see 3 is there. And there is one more, I think, that is common. I believe 6 there is common. All right. And therefore, those are the common factors of 12, 18, and 30. And the highest of these common factors is 6, as you can see. All right. And so we will write the HCF of 12, 18, and 30 is actually 6. Okay. Right. Now I want to remind you of something. We don't like working with doing tedious jobs. How would we find the factors of 376 and 343? Well, listing the factors of 376 and of 343 is going to be a tedious job that I do not want to do personally. And as a mathematician, we must think about faster ways of getting this without all that process. Okay, so we are going to try to do that. But before we get there, let's introduce prime numbers and what we mean by prime factors. Okay, so by definition, a prime number is any number that only has got 2 factors, and these 2 factors are 1 and the number itself. Okay, so a prime number, which we will symbolize with letter P, has only 2 factors, one of which is 1 and the other one being the P itself, the prime number itself. Okay, so clearly 7 is a prime number because 7 can be divided by 1 and by itself, and therefore 7 is a prime number. Okay, while 1 is not a prime number because the factors of 1 is only 1. So there is only one factor for the number 1, and it is for this reason that 1 is not a prime number. Many students sometimes confuse 1 as a prime number. Well, I'm telling you now that 1 is not a prime number if we go by this definition, because it only has one factor, which is 1. It needs to have 2 factors, right? List the first, well, I'm listing the first 10 prime numbers. You can pause and list the first 10. Actually, there is a point where I want you to be able to list the first 50, even the first 100 prime numbers. You should be able to list at least 50, I mean not 50, but the prime numbers lying between 1 and 50. You should be able to list those. Okay, so the first 10 prime numbers here are, hoping you already did it, must be 2, 3 is a prime number, then we have 5, 7, 9 is not a prime number, so 11, 13, 17, 19, 23 and 29. Notice 27 is not a prime number, 21 is not a prime number, 25 is not a prime number. So prime numbers are not necessarily odd numbers. All right, not all odd numbers are prime numbers. You can see there is an even number there. In fact, 2 is the only even prime number. The rest are odd, but not all odd numbers are prime. Okay? Okay. Now let's talk about what we mean by a composite number. So we know what we mean by a prime number and what is a composite number. A composite number is any number that has got three or more factors, including 1 and the number itself. Okay, so for example, 6 is a composite number because its factors are 1, 2, 3, and 6. It has got 4 factors, including 1 and itself, 1 and 6. So 6 is a composite number, a number made up of different factors, right? So by definition, a composite number, which we will symbolize by letter C, has 3 or more factors. Okay, so clearly 1 is not a composite number, okay, because it does not have 3 or more factors. And a prime number is not a composite number because it doesn't have 3 or more. A prime number will only have 2. So if it has only 2, then it cannot be a composite number. Okay, so all numbers other than 1 and prime numbers can be referred to as composite numbers. Okay, so 4 and 6 are clearly composite numbers because 4 has got 1, 2, and 4 as prime factors. It has got 3 prime factors, so that makes it a composite number. 6 is a composite number because it has got 4 factors. Okay, every other number which is not 1 or prime is a composite number. Now let's talk about prime factors. Okay, now we know what factors are. The numbers that can divide 8 are the factors of 8. But for it to qualify as a prime factor, it must be a prime number. So prime numbers that will divide another number are referred to as the prime factors of that number. Okay, example, 10. What numbers, which prime numbers, not just any number. We know 1 can divide 10, all right? We know 1 can divide 10, 2 can divide 10, 5 can divide 10, and 10 can divide 10. But not all of them are prime numbers. Not all those factors are prime numbers. So we are only interested in the prime numbers that will divide 10. And one of those numbers that will divide 10 that is also prime is 2. And the other one is, of course, 5. Okay, so 5 will divide 10 twice, and 2 will divide 10 5 times. And so we can conclude that the prime factors of 10 are 2 and 5. Okay, so these are called prime factors of 10. And we can express a number 10 as a product of its prime factors, like that. Okay, similarly, 18 can be expressed as a product of the prime factors that multiply up to get 18. All right, the first one there, we always try with the first prime number. So if you remember the list of prime numbers, it was 2, 3, 5, 7, and then we had 11. So we go in that order. So we try to divide by 2, and of course 2 divides it, okay, to give us 9. But 9 is not a prime number, so we'll keep that as a box, all right? But 9 itself can be expressed as 3 times 3, all right? And for that reason, we can say, we can write 18 as a product of these prime factors. So 18 is equal to 2 times 3 times 3, or if you like, 2 times 3 squared, okay? So these are referred to as the prime factors. These are the prime factors of 18, and these are the prime factors of 10. Any number, any composite number can be expressed as the product of prime factors. Okay? Here are the examples. I'm just writing them directly. Please try and check that these are in fact the prime factors for these numbers. So the prime factors for 4, well, 4 is 2 times 2, which we can write as 2 squared. Okay? 6 can be expressed as 2 times 3. All those are prime factors. So 2 and 3 are prime numbers, and they are prime factors of 6. Okay? 12 can be expressed as 2 times 2 times 3, or if you like, 2 squared times 3. And so 2 squared and 3, or 2 times 2 and 3 are the prime factors of 12. Okay, lastly, 20 can be expressed as 2 times 5, which can be expressed as 2 squared times 5, and these are the prime factors of 20. And so you can be asked to express a number as a product of its prime factors. If you're asked to express 20 as a product of its prime factors, then you have to express it like this. Okay? Question number 3, coming from a previous section. Express the following composite numbers as the product of their prime factors. The first one there is 28, 42, and 54. And I think we're going to use these numbers in the later part. Okay, what are the prime factors of 28, 42, and 54? Please pause the video and try this question out, and then check if we get the same answers. So the prime factors of 28 are, all right, we start with 2. 2 does divide 28 to give us 14, right? But 14 is not prime, so we have to divide it again. We try if 2 can go in again, so 2 can still divide 14 to give us 7, and 7 is now a prime factor. And so we can conclude that the prime factors of 28 are 2 squared by 7. Okay, so expressed as a product of prime factors, 28 is 2 squared times 7. All right, let's see the next one. What about 42? Again, start from the smallest. Does 2, the prime number 2, go into 42? And the answer is yes. It goes 21 times. All right. We try with the 2 again. Does 2 go into 21? And the answer is no. If we divide 21 by 2, we get 10.5. So 2 does not divide 21 completely. Okay. And so we go to the next prime number, which is 3. Does 3 go into 21? And the answer is yes. 3 goes into 21 7 times, and 7 itself is a prime number, so we stop there and we conclude that when expressed as a product of its prime factors, 42 is 2 times 3 times 7. Okay, 42 has been expressed as the product of its prime factors. Right? Next, what about 54? Similarly, we start with the smallest. 2 goes into 54 27 times, and 2 does not go into 27. Instead, it is 3 that goes in 9 times, and so we try with 3 again, and 3 goes into 9 3 times. Okay, and the 3 there now is a prime number, so we can conclude that if expressed as the product of prime factors, 54 can be written as 2 times 3 cubed. 3 times 3, 3 times 3 times 3, so that is 3 cubed multiplied by 2 there. Hope we are understanding this. Now we can talk about LCM and HCF of large numbers. Okay, we said that we don't want to use that tedious method of trying to determine LCM and HCF by listing factors like we did. So how can we do this in a faster way? Here is how to do it. All right, the ability to express numbers as the product of their prime factors is going to be useful in determining the LCM and HCF of large numbers. Okay, in fact, we can find the LCM and HCF all at the same time in one quick process. Okay, let's see that. Example, for the composite numbers 28, 42, and 54, which we did earlier, let's find the LCM and the HCF. Okay, we're going to get this in one big step. All right, so to do that, pause the video and try it out if you know how to do it the quicker way. I won't ask you to do the long way because that would be very tedious, so let's not waste time there. Try it out if you know how to get these numbers quickly in one step. Okay, and now let's begin. So the first thing we want is, of course, to remember that we had already expressed all the 3 numbers as products of their prime factors. I believe I have written them somewhere. So 28 is 2 squared times 7, 42 was 2 times 3 times 7, and 54 we found that as 2 times 3 cubed, like that, right? We'll put those up there to remind us. Next, we make a table of prime numbers with the composite numbers represented in prime factor format like this. So we make a table. We will keep our numbers on this side so that we can use them on the table. 54 was 2 times 3 cubed. So we make a table like this. At the top, we list the prime numbers. So here we are listing the prime numbers that are represented. Now you can see here there is no 5, but I've just put it there so that we can see how to include it in. We're going to see why we don't really have to include the 5 here. But we have listed all the prime numbers from the smallest that we see here to the largest. So the smallest there is 2 and the largest here is 7. So we can list all the prime numbers from 2 to 7, although we don't have to list any prime number that is not appearing. But if we put it there, you will see how it functions in the process, right? So we put the prime numbers horizontally there, and on this side we put the composite numbers whose LCM and HCF we are seeking. So we will put there we'll put 28 there, we have the 42, and we have the 54, okay? So here we will put the composite numbers, and on this side we'll put the prime numbers, okay? That are represented when we write the composite numbers as products of their prime factors, okay? Now what we do next is we represent. So 28, there is a 2, the prime number 2 is appearing, but how many times? It's appearing twice, so it's appearing as a square. So we put 2 squared under the column of prime number 2, so we'll put 2 squared there. There is no 3 appearing for 28, so we can put 3 power 0 because 3 appears 0 times, 2 appears twice, it's 2 times 2, 3 appears 0 times, so we can put 3 power 0. 5 does not appear there, so we can put 5 power 0. And 7 appears 1, so we can put 7 to the power of 1. Okay, do the same with 42. 42, the prime number 2 appears 1, so we can put 2 power 1 there. The prime number 3 appears 1, so we can put 3 power 1 here. The prime number 5 does not appear, so we put 5 power 0 there. The prime number 7 appears 1, so we can put 7 to the power of 1 there. And we repeat the same with 54. The prime number 2 appears 1, so we can put 2 power 1 there. The prime number 3 appears 3 times, so we put 3 power 3 there. The prime number 5 does not appear, so 5 power 0. The prime number 7 does not appear, so 7 power 0, like that. Once we make this table, we can read our LCM and HCF directly, like this. To find the LCM, we go for the largest power. Okay, so to find the least, we go for the largest. And to find the HCF, the highest common factor, we go for the lowest powers. Okay, like this. So to find the LCM, we go to each column and pick the largest power. So we can see that the for column of prime number 2, the largest power is square, right? So we will pick that one. So we are going to make the LCM, select and multiply all factors that have the largest powers from each prime number column. So the largest power here is 2, the largest power here is 3, right? The lower one there. Here we can pick any of them. After all, it's just 1. 5 power 0 is 1, so all these are just 1s. And here the highest is 7 power 1, so we can pick any of them. So to find the LCM, we go for the largest powers. It's like doing the opposite. Least common, go for the largest or the biggest power. Okay? So under prime number 2 column, we pick the largest there, which is 2 power 2. And the next column, the highest power there is power 3, and so we go for that. The next column there, every one of the numbers there is 1, so we can pick anything, any of the 3. And in the last column there, the largest power there is 1, and so we can pick any of them, any of the 2. And so the LCM then, therefore, the LCM of 28, 42, and 54 is 2. 2 squared times 3 power 3 times 5 power 0 times 7 power 1. Okay? Alright, I've just left 5 power 0 because it is 1 anyway. Alright, and if we multiply that out, we will get the LCM to be 756. Okay, it would be very, very tedious to try and list all this, 28 times 1, 28 times 2, 28 times 3, all the way up to 756, and then do the same for 42, and that's a very, very tedious work that we do not intend to do. Okay, and so that's how we find the LCM of 28, 42, and 54. Within the same table, we can also find the highest common factor. Now, for the highest common factor, we go for the smallest. So if we are talking highest, here we go for the lowest power. Okay, it's the opposite of one another. So on the same table, now we look at each column and pick the lowest power. And therefore, you can see that the lowest power from this column for prime number 2 is 2 power 1. Okay. From the next column, the lowest power there is 3 power 0. From the next one, it is 5 power 0. And from the next one, it is 7 power 0. We go for the lowest power. Okay. So it does help to include this, even if there is none, it helps to put 3 power 0 there if there is no 3 as a factor of 28. Okay, and so all we need to do is multiply those. Okay, and therefore the HCF of 28, 42, and 54 is 2 power 1 times 3 power 0 times 5 power 0 times 7 power 0. Now 3 power 0, 5 power 0, 7 power 0 are all ones, and so therefore the HCF is just 2. And that's how we find LCM and HCF for very large numbers. Okay, let's see if we understand this. Here's an exercise. You will pause the video and try the questions out yourself, after which you check what my solution is. Express the following as the product of prime factors. Okay, 40, I think 72, and 98. Express each of them as the product of prime factors. Okay, secondly, find the least common multiple of 84 and 120. And lastly, I want you to find the highest common factor of 56 and 70. So the three questions are not related, but they are all testing your ability to eventually determine LCM and HCF of large numbers. Okay? Pause the video, try it out. Assuming you have done so, these are the answers you should be getting. The prime factors that are multiplied to give us 40 are 2 power 3 times 5, and for 72 it's 2 power 3 times 3 squared, and for 98 it is 2 times 7 squared. Right? Try those out and check that you're getting the same result. What about the LCM of 84 and 120? If you've done this correctly, you should be getting the LCM is that 2 cubed times 3 times 5 times 7, which turns out to be 840. And the HCF of 56 and 70 are 2 times 7, which is 14. Okay? Hope you got that right. Let's go to the next question. Exercise B. Two buses A and B both use the same bus stop. Okay, bus A runs every 10 minutes and bus B runs every 14 minutes. So runs every 10 minutes, that means the next time it runs will be 20 minutes, then 30 minutes, multiples of 10, right? This will run after every 14 minutes, so after 14 minutes, the next time it runs is 28, and so on, right? So those are multiples. Both buses are at the bus stop at 11 a.m. The question is, what time will both buses next be at the bus stop? Okay, pause the video and try the question out. Okay, now to answer this question, you have to when you read this, think of the bus running. If it runs every 10 minutes, that means we can tell when it will next come in. It will be after 20 minutes, then after 30 minutes. So we are actually talking multiples, all right? And the question is saying, when will the buses next be at the bus stop together? So the next, the word next there, the connotation there is that it's the earliest, the earliest time the bus will come in again. And when we are talking of earliest, we are talking the least, which is the connotation there again is we are talking LCM. So in fact, this question is just asking us to find the LCM, the least common multiple time at which the buses will be here again together. Okay, and if you do this correctly, you should find, if we're going to do that, we find the common, the prime factors of 10 is 2 and 5, and the prime factors of 14 is 2 and 7. And so if we're looking for the LCM, using the method we used earlier, you should be able to tell that the LCM is 2 times 5 times 7, and that is 70. All right, so 70 minutes. So the next time they are in together is 70 minutes after 11 a.m. And what time is that? We have to add 70 minutes to 11 a.m. That is 60 is 1 hour. So that takes us to 12 noon. And there is 10 minutes left there. So the next time they come in will be 12:10. The next time they are in together is going to be 12:10. I hope you understood that. Exercise C, or question C if you like. Light A, so some light flashes every 8 minutes, and light B flashes every 20 minutes. And the question is, both light flash at the same time now. And so the question is, work out how long it will take for both lights to flash at the same time again. So again, we are talking of when next will they flash together again. We are talking of LCM. All right, to do that, we look for the prime factors of 8 and prime factors of 20, and then determine the LCM. If we do that, hope you paused the video and tried it. If we do that, we should have an answer for the LCM of 2 cubed times 5, which is 8 times 5, which is 40 minutes later. So if they flash now, the next time they flash together will be 40 minutes from now. Okay? Question D, once again, you will pause the video and try the question out yourself and then see my solution. This time we're given two numbers as the product of their prime factors. So 648 is 2 cubed times 3 power 4, and 540 is 2 squared times 3 cubed times 5. The question is, what is the LCM and HCF of these numbers? Okay, write down the HCF of 648 and of 540, and like we said, you can make the table, or you can see if you check if you can see them directly. And so we can say, so that is, the first one was to find the HCF, the second one is to find the LCM. So when it is LCM, we go for the larger ones. So here we have 2 power 3 and 2 power 2, so we would go for 2 power 3, and for 3 this is power 4 and that is power 3, so we would go for power 4 and so on. And this is 5 power 0 and this is 5 power 1, so we'd go for 5 power 1, like that. So let's answer this question then. Pause it and try. Okay, so the HCF then is going to be, like we said, we pick the lowest power. So for 2 we will take 2 power 2, and for 3 we will take 3 power 3 because that's smaller than this. And for 5, this is 5 power 1 and there is a 5 power 0 there. And so this must be the HCF, okay, which is 108, 4 times 27. Okay, and the LCM is, for the LCM, we pick the higher powers, all right? So for 2, we will take 2 power 3, and for 3, we will take 3 power 4, and then we'll take 5 power 1 because the other one is 5 power 0, and when we multiply that, we'll get 3240. So those are the LCM and HCF of the number. So clearly, when we express each number as a product of their prime factors, then it becomes much faster to find the LCM and the HCFs. All right, let's see another question E. And number A is given by 2 squared times 3 times 5 squared. And the number B is given by 2 cubed times 3 squared times 7. And the question is for you to write down the LCM and the HCF of A and B. Okay, so once again, pause the video and try to find the LCM and HCF of A and B. Assuming you've done that, you should be able to see that the HCF is 2 squared times 3. Of course, those must be the lowest powers. 2 power 2 is lower than 2 power 3. 3 power 1 is lower than 3 power 2. 7 power 0 and 7 power 1. 5 power 2 and 5 power 0. So we are going for the lowest values, and therefore we will keep 2 squared and 3 there like that. And so our HCF is 12. What about the LCM? The LCM, now we take the highest powers, and the highest power is 2 power 3, 3 power 2, 5 power 2, and 7 power 1. So we have to take all of those, and the answer is going to be 12,600. Lastly, I believe, Jacob thinks of two numbers greater than 10 and says that the HCF of the two numbers is 7 and the LCM of the two numbers is 84. Okay, the question is, write down the two numbers that Jacob has in mind. So which are these two numbers Jacob is thinking about? I'm going to let you think about the solution to this, and if you get the correct answer should be, if the two numbers are greater than 10, then the two numbers are 28 and 21. Okay, this I believe brings us to the end of this discussion on LCM and HCF. I hope that you found this useful, in which case please consider liking the video, and if you've not already done so, please subscribe to the channel and share this with other students that who might also find this useful. Okay, I will see you in the next video. Thank you very much.